Hello everyone, welcome to the final lecture for week 9. So we will be discussing about automatic prompt engineering in this lecture. So and we will focus on two different aspects of this, discrete prompt search and prompt tuning. Okay. So what is the need for automatic prompt engineering? We have talked about interesting design aspects for prompts, right? And we have talked about so many things. But why is there a need for automatic prompt engineering? Right. So what is the idea? Typically, what we do with the prompts are typically designed by humans, right? And they may not be optimal because prompts you can see as a prior that you are giving to a language model, right, for doing a particular task. Now, this is a starting point for the language model. So once you give a prompt, after that you will put the input. So it will go in a particular direction, right? Because you can put your attention on the prompt and start generating. But the human design prompt may not be always optimal. So what we do in automated prompt design, we will try to do certain more search and try to generate more effective prompt templates, right? So in some predefined search space, and this would be much more complex because you need to now see the search procedure. How do you search from different possibilities in different spaces? Generally, it has been seen that it outperforms the manual prompt engineering. Why? Because you have done much more search here, right? And you have even seen what happens if I do this particular prompt on my final output. So now there are various approaches. For example, you can start with some prompt, paraphrase these, and keep on checking their performance on some validation set, right? So that may be one approach. Or you can do gradient-based discrete prompt search. So I am saying discrete because now you will search in the token space. You see what is the sequence of tokens. So this is a discrete space. You see what sequence of tokens will help me obtain the best possible prompt, gives me the best output. Or you can do prompting that's in the continuous space. So we will see say prior. So why don't I just use soft prompts? So these will be soft prompts. Okay. So we'll talk about these techniques and how do these give you much more effective prompts for your task. So what is prompt paraphrasing? Paraphrasing is an easy idea. I mean, you take with an initial prompt or prompts that are already there in your database and use some paraphrasing model to create many paraphrases for these prompts, right? And then you can find out which of these are better at a certain development set, right? So this is a very simple scenario. But there are more complex scenarios. For example, gradient based discrete prompt search, and this is where this came in this paper auto prompt, right? So and this was applied to a simple masked language model like BERT, right? And for tasks like sentiment analysis and all. So let's see what it actually does. So sentiment analysis, you will have an input like this, a real joy, that is a sentence, your input. Now what you do, you say, okay, I want to apply a prompt to this. Now prompt will be a sequence of tokens. So let's say I want 1, 2, 3, 4, 5 tokens in my prompt, right? So these are called trigger words. So I have some 5 tokens that I want. I don't know what are the ideal 5 words that will give me the best possible prompt. And then you say, okay, once I have these 5 words, like this is the one that they got, and this generally may not make sense in general. I mean, nothing to do with sentiment analysis, atmosphere, a lot, dialogue, clone, totally, right? I mean, no human will come up with something like that. But they come up with a prompt like this by doing a search in the discrete space, and they say, okay, so this is my prompt. So this is the input. This is the prompt that I had identified. Now I need to do classification. I use my masked model. So I say, okay, masked language modeling. And another interesting thing that they say, okay, from there I'll get the probability distribution over all the words, right? Now they will say, okay, among all the words in the vocabulary, I will select some words as the label word for different classes. So I say here there are 2 classes, positive and negative. So they find, okay, Again, they may not completely make sense because this also has a search procedure. Chris, marvelous, marvelous actually makes sense. Philanthrop. So these three are the label words for positive class, and worse, incompetence, worse, they also seem to make sense. They are for the negative class. Right. So what they will do, they will only compute the probability for the label words for the positive class. Right. Add that up. Compute the the probability for the label words for negative class. Add those up, and this will give you the probability for the positive and negative. Okay, and this gives you the probability that what is the whether I'll predict a positive class given this input and the prompt, or whether I'll predict a negative class given the input and the prompt. Right. So you see there are two interesting search procedures here. How do you identify this particular prompt, right? And how do you identify this particular label words, right, for each class? Okay, so let's see how this method actually works. So you say, okay, so what is the number of trigger tokens is a hyperparameter. So this number is a hyperparameter. So you can say, okay, I will have some search. So I'll say maybe between 3 and 6. I'll choose some number. So here they are starting with 5 tokens. So they have taken 5 trigger tokens. Okay, so I need to initialize them with something. So here they all initialize them with mask tokens. So okay, I'll have a sentence, input sentence, mask, 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 and then I'll have a token to get the final. It's also like a mask, so from where you will actually compute the probabilities, right? Now, okay, I started with this start all masks, right? And then they say, okay, from my training data, I'll take a batch of examples. Okay, so I'll have a batch of examples, the inputs that I will use. Okay. Now, what I can do, I'll pass each example. So I'll put the sentence, I'll put the trigger, right? And using this token, the mask token, I'll get the probability for positive and negative, assuming you already know your label tokens. So we'll come to that. So let's say you know your label tokens for both the classes, so you can get the probability for y given x, right? So by using your label tokens. So okay, so this is possible. So I can get the probability of y given x for different classes, the positive class, negative class. I mean, y is actually known to you. So this is the sentence in training. So you know whether y is positive or negative. So you can compute the probability for your positive or negative class, right? So this is a single value just for the class that is there in the ground truth. Okay. So so I compute that. Next, what they do is something very interesting. They say, okay, now I have computed the probability of my class given this input. This was my all masks. Now what I will do, I'll take the gradient of this, the loss. What is my log? Minus log probability of y given x. So I'll take the gradient of my loss with respect to the jth trigger token. So you take the jth trigger token. So xtj, jth trigger token. So I compute the loss with respect to token that I can do. I mean, it's all differentiable, so I can compute the loss with respect to xt1, xtj, xti, whatever, right? I can do that. I can compute the loss with respect to each trigger token. Then they say, okay, then what will be the impact of replacing the jth trigger token by one of the tokens in vocabulary is captured by, so they say, okay, by swapping how much will be the change in the log likelihood by swapping the jth trigger token with another token in the vocabulary. So this they approximate as W in transpose. This is the input embedding. See, each word is fed to the transformer. So it has this 768 dimension if it is BERT based model, 768 dimension embedding, right? So this is the input embedding for each token. So 768 dimension embedding. So you multiply the input embedding, the embedding matrix for each word, that particular row or column. So with the gradient for this token, right? The gradient with respect to this token. Okay. And this will give an approximation to how much, if you replace this mask by this token, how much will be the log likelihood change, right? And you want to get top k words that will increase the log likelihood, right. So, top keywords that will increase the log likelihood. So, okay. Now, you may be wondering why this method, like why do you multiply this input embedding? Input embedding is a change that you are doing, right. So, this is the change you are doing because you are replacing a word with another word. This is the change you are bringing in. You could have, of course, done WN transpose minus the previous word, but in this paper they didn't do that. They just use the input word times the gradient. Like, why does this capture the, is a good approximation for increasing the log likelihood, right. So this actually comes from directional derivatives, right. So, and it's a first order approximation. So, what is the idea? So, suppose you have a differential function f, right. So, this is a log likelihood in your case, right. So, you want to see how much is the log likelihood increasing by making it change or by going in the direction of one particular trigger token swap, right. So, if you really say differentiate the function with respect to a particular trigger token, like particular vocabulary token. So, this will be the differentiation, right. Now, if you simply do an approximation, they say okay, that means f x plus epsilon v is the how much you have gone in a particular direction. So, b is the direction, epsilon is the amount you have gone in the direction, minus f x divided by epsilon is roughly the gradient of f x in direction v, right. That means the amount of change is f x plus epsilon v minus f x is approximated by epsilon times the gradient, right, and that is where the expression comes. Epsilon is the change. What is the change? WN transpose, and what is that? The gradient with respect to the trigger token, right, in that direction. So, trigger token j of the log py given x. Okay. So yeah, I mean that's how this idea comes. So, you can use this formulation to have an approximation. See, otherwise what you will have to do, you will have to actually change your prompt by putting this token and compute the log likelihood, and this is too expensive. You have to do it for all the tokens in your vocabulary. It's too expensive. So, it's an approximation. Say, oh, you have already started with some prompt, all masks. You can compute this very easily. Now, once you have this gradient, you multiply this with all the embeddings for all the tokens, and this gives an approximation which keywords will have the maximum impact, and you only select the top keywords. So, you avoid actually changing your prompt with each vocabulary. This will become a huge search procedure, I mean, and then computing the log likelihood on some example. I think this will be too cumbersome, I mean too expensive, and this is much easier process. Okay. So, that is how we use this particular form of equation 2. Good. So, now so that what we will do, so what will happen after this? So, I will find some k tokens per word. So, I will find some k possible replacement here, k replacements here, I mean k possible replacements here, and then I will compute the probability of y given x prompt. That is, if I put that prompt, now I will go to my validation set and say okay, fine, you have given me this particular prompt, is this a good candidate? So, I will compute the probability of the class, right, from my validation set, and see which of these are good candidates, right. I mean, in general I may have k to the power if there are n words in or t trigger tokens, k to the power t, right. I will have k to the power t possible prompt variations, and for each prompt variation what I will do, I will put the input, I mean in the validation set, I will take a sample of validation set, I will put the input, I will put this prompt, one possible prompt, I will compute the what is the probability of the actual classes, right. On the whole validation set, what is this probability I am getting for the correct class. But you see, even that is very expensive. You will have to do it for all k to the power t possible prompts, that is possible prompts. This is small because you have to compute the probability for only some 3 to 5 words, right. So, and add that up, that gives the probability for the class. but can I even further simplify this rather than doing k to the power t? So they said, okay, I mean, this scenario is very similar to beam search. So rather than doing all possible exhaustive search over each top k, what you can do, you can do a beam. So you will say first k, again you only choose, you will have k squares, so only choose k, like that. Right? So you can augment this replacement strategy with the beam search. So you will take top k token candidates for each position, and you search left to right, right? So you'll have maintain top k at the left, and then you will have from each of the top k you will have k k each, and you will put this sequence so that you have only k sequences in each time, right? And for each sequence you will compute this probability. Okay, fine. So so this is what the paper did, and the out of prompt paper. And then another thing that we have not talked about is how do you select this label tokens, right? This set Vy. So remember what is happening. So once you have this final, so you put this input, and then you have the prompt, right? And you have the mask. So so they say, okay, let me not put this prompt at all, just put the input, right? So after input sentence, I'll have a mask, and now I'll pass it through a BERT model. So I'll get the final h of this hidden vectors for mask, right? Hi, right, at the final layer of the BERT. Now I will have a simple linear layer that say, okay, so y is one particular class. So let's say this is y is, I replace y with positive, right? So C plus, positive class. So I'll say, okay, what is the probability that it will give me a positive class? I'll multiply this with a vector y and a bias beta y. I mean, how does it come from? I mean, the idea is simple. So you have this hi, that's a 768 dimension vector. Now you want to get the probability for two classes. What do? You have 768 cross 2 matrix, and of course there are two bias scalars, right? So let's focus on the matrix. So you will have 768 cross 2 extra parameters, right? So you can think of 768 cross 1 for one and 768 cross 1 for another one, right? So you can break that into two parts, 768 cross 2, right? 768 cross 1, another 768 cross 1, one for positive class, another for negative class, right? So this particular vector, this is for positive class, 768 cross 1 is your vector for, say, C plus class, and you will have a corresponding scalar also, right? The bias term, so beta for C plus class, right? And this actually gives you the probability. I mean, this is proportional to the probability, right? You will simply apply softmax over whatever is the output here. So this is proportional to the probability for the class. So we will get two vectors. So if you have positive and negative class, you will get a vector C plus and bias for C plus, and you will get for C minus a vector, right, of the same dimension hi and a bias, a scalar bias for the minus, right? Now you want your label BERT. So idea will be a label BERTs will be something that are very similar, I mean, in the embedding space to this y, right? So some vectors that are very similar to this particular output vector, right? So what you do, you say I replace this yi with my w out, the out embeddings. What are the out embedding? The unembedding matrix, right? So you may not tie this with your embedding matrix, so you may have a separate output embeddings for each word. So right, so how do you go from 768 dimension to your vocabulary? You have an unembedding matrix, right? So you take the output embedding for each word, right? So each word in your vocabulary, you will have 68 dimension, 768 dimension embedding. That's your out embedding. So you say, okay, the score for this class, say positive class, for a particular word, right, like fantastic, will be the probability of predicting this y class given this w out, and what is that given by? You replace hi with w out. So this will be simply w out for fantastic dot this y that you have got, the positive class vector, plus the scalar for positive class, right. So this will be proportional to that. Now this is core. So essentially, I mean, because this is common to all the words, so essentially the words that are most similar to this vector would feature in the label class, right. So that's how you take some top keywords as per your set that you want, the label set, and you can predict. So this is how you will do it for positive class. Similarly, you will do for negative class, right. That's the idea. You get your label words. You can try this problem that suppose you are using this auto prompt with BERT for text classification with two classes, say positive and negative. Now, so what are the number of learnable parameters? So assume you use Vy equal to 3, right. So let's not worry about explaining, but you suppose you want 3 top words and you have 2 classes. So what are the number of learnable parameters? So remember, this is what I have to do. So I have one y vector for each class, and this has the same dimension as the final hidden vector, so 768, one for each class, one for positive, one for negative. So I have 768 cross 2 parameters, plus I have some bias terms, so 1 per class, so plus 2. So these are my number of learnable parameters. So once I have learned these parameters, then I simply take the W out embeddings and multiply, I mean, find out which of these W out are closest to this HI, sorry, closest to this Y for that class, and this will give me the class, the set Vy, the label tokens for a particular class. Okay. And they showed huge gains in performance. Like if you do manual, you see, I mean, 63, and if you do auto prompt, you go from 63 to 82. So Roberta manual 85, and you go auto prompt will take you to 91.4. Like huge gains just by this discrete search procedure. And these are the example prompts, and you see they may not make sense. Like sentiment analysis, writing academics where overseas will appear has no connection, but that's what makes sense. Positive legal tokens, partnership, extraordinary, blah, negative, averse, persistent, and unconstitutional. Analyze problem, you see premise, this is your mask, and then your trigger tokens, hypothesis, and they found nobody nor for contradiction. I mean, these are label tokens, and concrete empathic workplace, I mean, these are some label tokens. And they also tried it for things that were not just classification, but also retrieval and extraction, right. And you see, I mean, this procedure works, but it does not give you some interpretable things. And yeah, of course, this has a huge search procedure involved. Now, there are other methods for discrete prompt search that will give you more interpretable prompts, like Evo prompt, that is more like an evolutionary algorithm for that. So idea would be, suppose you have some manually designed prompts already with you, right. So what you can do, you can combine them and generate new prompts. So they do certain procedures that people do in genetic algorithms, like they will do crossover of prompts. So you will cross over these prompts and create a new prompt, and then you will mutate the prompt, right, mutate the prompt that you generated and get the final prompt that is bracketed with open prompt and end prompt, right. So so you see, I mean, you start with some prompts and you teach language model how to do crossover, how to do mutation, and then it gives you more possible prompts, right. And they also said, okay, we can even guide it better, saying that, okay, given 2 prompts, see what is important is which parts are changing here. So like categorize the tweet according to it, if it has a positive or negative sentiment, carry out sentiment analysis for every sentence to decide if it is positive or negative. So you say, okay, identify the different parts. So you say, okay, tweet versus sentence, and categorize versus carry out sentiment analysis. So you know, once you identify these parts, these are the possible candidates where you can do further modifications, right. So randomly mutate the different parts. So tweet goes to review, categorize, analyze, and so on, and then you combine the different parts with a new prompt, right. So you understood different parts, now you take a new prompt and you see where you can replace. Like here, you are in this class, you are given sentences, so you know sentence can be permuted, so you say reviewed. So you are guiding the LM a bit more, and then finally you do do a final crossover with this step 3 prompt, with a basic another prompt. So you have more prompts here, but you also do bit more guidance. So you can do evolutionary algorithms for also doing this prompt search. Okay. So finally, I'll end with soft prompts, the prompt tuning part. So here we are not searching in a discrete space, but we are searching in a continuous space. So idea would be can you optimize the embedding of a prompt instead of the words, right? So why is that important? So let's say you are doing fine tuning of model, like a model which has 11 billion parameters, and you're fine tuning it for multiple tasks, right? So what will happen? So you will have a different. So see, we start from some pre-trained model, but when you fine tune it for one task, I'll have theta fine tuned for task 1. Another task, I'll have theta fine tuned for task 2. I'll have separate parameters per task. And suppose your model has to cater to different tasks, you will have to store all of these parameters, right, at inference time if you want to cater to multiple such tasks. And that means you have many such copies of these 11 billion parameters, right, that you have to store. Now what prompt tuning does, it says, okay, you don't fine tune your parameters, So we go by the idea of prompting, right? So you can have a task specific prompt, and this prompt can be fine tuned, right? And for it to be fine tuned, it has to be a soft prompt. That's the idea. So what you'll do, so for each task you will have a prompt. So say your prompt is some 10 tokens, right? So you will have some 10 cross 768 if you are doing with 768 model dimension. So these many parameters you have extra per task, right? So for task T1, same parameters for task T2. You tune these parameters, and then apart from this pre-trained language model, you only need these small number of parameters, right? You say just 20,000 parameters for each task separately. So what exactly happens in prompt tuning? So let's say you are given some n tokens, right? This is your input. So you will have a matrix n cross e. This is the E is the embedding dimension. So what will be our soft prompts? This will be another parameter like p cross e. Let's say p is my length of the prompt. So p is your length of the prompt. That means you have p tokens in the embedding space. So you will have p. Each token will have e in the embedding space, right? So p cross e. So think of each as a token which has a learnable embedding. So this is of dimension e. This is separate from the embedding matrix. So I want to learn these, right? So I have some. So for each token, so say T1 to TP, I'll initialize and say E is my embedding dimension, E dimension vector, and I want to find out what is the best value for this E dimension vector. So I have P cross E parameters to be trained, right? So what I will do, I'll put this before my input. So my input becomes P plus N cross E, and then you can go through the normal encoder decoder. So this is like prompt, you put it before the input, but these are now learnable parameters, and you fine tune the model, but only these prompts, right? You don't touch your other weights, right? You only tune the prompt. You don't fine tune your query key and other matrices, nothing. Only this much you tune. Okay. So only the prompt parameters are updated. Okay, and what they found out, so this is the standard model tuning of the model and doing multitasks, and you see, I mean, this is the number of model parameters. So if you keep on increasing the model parameters, at some point this prompt tuning, this the green curve, comes very, I mean, roughly becomes similar to the model tuning, right? For large models, you can simply do prompt tuning and match the performance of model tuning, right? And this is much better than prompt design, because prompt design manually would not be optimal at all, right? So this was something very, very interesting, that they found that you can achieve strong performance by model tuning, but you need separate copies of the model for each end task. So prompt tuning matches the quality as the size increases, while enabling the reuse of the single frozen model for all the tasks, plus some additional very minute number of parameters for each soft prompt, and it outperforms the few shot of GPT-3, right? So this was very, very interesting, and we will talk about more. This is like one sort of parameter efficient fine tuning method. because we did fine tuning here, but with the just making use of prompts, right? So you can talk about this, try this problem. For example, I'm using T5 model dimensionality 1024, 24 layers, and I'm tuning it for 3 tasks: text summarization, question answering, and text simplification. So you can use full fine tuning. So how many parameters do you need? So T5 has encoder, decoder. So remember, encoder has 12D square into L, decoder has 16D square into L, right? So total 28 into 1024 square into 24. That many parameters, right? Per task you have to store. So these many parameters per task. So into 3, right? This will be for full fine tuning. But if you use soft prompts of length 10 for each task, so that means I am using for each task length 10, x1 to x10, and each token will have a learnable embedding of dimension, same as model dimension, that is 1024. So let 1024 cross 10, that many parameters per task, so roughly 10k cross 3 for 3 tasks. You see, it's much smaller than what you are doing with full fine tuning. So that many extra parameters you will have to store at inference time apart from the T5 parameter. Of course, T5 parameters have to be there because you will only put that prompt, but then you have to have the T5, but you are not storing multiple copies per task. Okay, and you could avoid tuning all the parameters. You could still use your T5 copy and have an additional thing per task. Okay, so that also, this is nicely also given in this book, Large Language Models, a Deep Dive, right? So this can be a good reference for this particular lecture. This also ends up a week 9. We will start more about parameter efficient methods in week 10. Okay, thank you.